Greetings. Welcome to the 24th lesson in a series of lessons on the basics of power systems engineering. In this lesson, I will work through a numerical example of a balanced three-phase system consisting of a generator, a wye-connected impedance load, and the connecting lines. In the next lesson, I'll show an example that features a delta-connected load. Since there is not enough space on the slides for both the statement of the problem and the lines of solution, I'll state the questions of this example verbally. We're looking at a balanced system with per phase load impedances of 80 plus J 60 ohms and per phase line impedances of 2 plus J 10 ohms. To reduce clutter on the diagram, I have marked only one load impedance. The other load impedances are identical to it, and only one line impedance, and again, the other two impedances are the same. The generator voltage is given as 4800 volts. We're asked to find the line currents IA, IB, and IC, and the load voltages VAN, VBN, and VCN. The voltage drop at the load compared to the source voltage in percentages, real and reactive power delivered to the three-phase load, P and Q into the load, and real and reactive power lost in the lines, P line and Q line, and real power efficiency of these lines. When the voltage of a three-phase system is given absent any other information, it should be taken to be the line-to-line voltage, and of course the value is always given as an RMS value. The generator should be assumed to be generating positive sequence voltages unless it's specified to have been set up as a negative sequence generator. Since for any power system we are allowed to assign one voltage as a reference voltage with zero phase angle, we might as well take the 4800 volts with zero angle to be VAB. Here it is, VAB equals 4800 volts, and it's implied that its phase angle is zero. The easiest way to analyze a balanced three-phase system that connects a Y-configured generator to a Y-connected load is to draw the equivalent line to neutral diagram of a single phase of the system, find the answers, and then extend the answers to the three-phase system. I've symbolically separated the equivalent line to neutral diagram of the A phase of this system. That would be this circuit here, and I have actually pulled it down and drew it separately on the next slide. Here's the equivalent line to neutral circuit. Since in the balanced three-phase operation neutral carries zero current, its impedance does not matter and is not given, we can treat it as a zero impedance link here. Let's first find the line to neutral generator voltage, VAN, either there or here. We know that in a positive sequence system, VAB leads VAN by 30 degrees, and its magnitude is the square root of 3 times the magnitude of the VAN, as shown in this equation here. From this, VAN is calculated as VAB over square root of 3 with negative 30 degrees of phase angle. Substituting 4800 for VAB, we'll have VAN equals 4800 over square root of 3 with negative 30 degrees, which comes to 2771 volts with negative 30 degrees phase angle. We can now calculate IA, as Vn over sum of the line and load impedances. (2,771) with negative 30 degrees over the sum of the line impedance and the load impedance, each as a single phase quantity. And IA comes to 25.7 amps with negative 70.49 degrees of phase angle. Let me summarize the two results we have found so far, VAN and IA. Load voltage is found by multiplying the current IA by the load impedance. We have both of these. And VAN equals the product of the current and the load impedance. We are looking for the line to neutral voltage of the load. And that one comes to 2,570 volts with negative 33.62 degrees. Multiplying VAN by square root of 3 and adding 30 degrees to its phase angle will give the line-to-line voltage VAB, which is one of the questions of this example. And doing the math here, adding 30 degrees, multiplying by square root of 3, gives us 4,451 volts with negative 3.62 degrees of phase angle. Once we have VAB, VBC is found by taking away 120 degrees from this phase angle, because our system is a positive sequence system, and VBC lags VAB by 120. Here it is. And we can find VCA by taking another 120 degrees from VBC, which is shown here, or we could have had it by adding 120 degrees to VAB, and that's this angle here. I prefer the magnitudes or the absolute values of angles, phase angles, that are between 180 and negative 180. So if we ever come across a absolute value of phase angle that's over these values, we can always add a 360 to the negative one, or subtract a 360 from a positively large phase angle to get them between these two limits. Summarizing the results so far, we have the line-to-line voltages of the load, and we have one of the phase or line currents. But having IA and knowing that the system is positive sequence system, IB is found by simply subtracting negative 120 from this, which is equivalent to rotating this phasor by 120 degrees in the clockwise or negative direction. And that comes to same magnitude, of course, with this phase angle. And again, by adding 120 to this angle, we'll get IC. 25.7 amps with 49.51 degrees of phase angle. Let me pull everything up so that we have room for further work. Here they are. The percent voltage drop can be calculated by comparing line-to-line voltages between source and load, or by comparing line-to-neutral voltages between source and load again. But the answer will be the same. I'll be using the line-to-line voltages. So voltage drop in percents equals source voltage line-to-line minus load voltage line-to-line divided by source voltage times 100. And for our example, it comes to 7.3%. Remember to use only the magnitudes of the voltages. The phase angles should be left out. Next, I'll find the real and reactive load power. But let me first go back and make a note of the line to neutral load voltage that was calculated earlier, because we're going to need that. And here it is, VAN plus minus. Multiplying this line to neutral voltage by conjugate of the current, IA, will give us the complex load power for a single load. And here it is, S for single phase of the load equals VAN times IA conjugate. Well, IA was found to be this value. Its conjugate has the same magnitude, but the phase angle will have a sign that's the reverse of its sign, so it will go from negative to positive, as you can see here. The product written in Cartesian or rectangular format is this number, 52,856 plus J 39,642. Let's next find the per phase complex power loss of the line. We could find the voltage drop on across the line by multiplying IA times the Z line, and let me call it V line, and multiply this V line by conjugate of IA to find the complex power of the line. But it's easier, we can skip a step if we just use the other equation for S, and that is I magnitude squared times Z line. And that's what I'll do in the next slide. So S for each line equals magnitude of the current squared times Z line. And we have everything we need, 25.7 squared times the impedance of the line, and Z and S for the line comes to 1,321 plus J 6,605. To find the three-phase powers, we multiply each of these by 3. And here I have it for the load, showing as a complex number. And again, multiplying, I don't show it here, but multiplying the value for single phase complex power for the line loss by 3 gives us this value here, and they're summarized up here. The real parts of these complex powers give us the real or active power, and the imaginary parts give the reactive power. So for the load, real power is for three-phase, real power for the load of the load is 158.6 kilowatts. I just divided this by 1,000 to turn it into kilo. And also the reactive power of the three-phase load is 118.9 kilovars. And for the power loss of the line, we have 3.963 kilowatts of real power loss and 19.82 kilovars of reactive power loss. Now we get to calculating the efficiency, which will deal with the real power between the source and the load. And we know efficiency is the power that goes out to our load divided by the power that comes into our system from the source. So dividing, let's call this P out, P in. The ratio times 100 gives us the efficiency, and here it is, equals the load power, I took it for the three-phase, which was found in here, divided by the power that the generator has generated, or the power in. This is power in, out, and this is power in. The power in, or the power that the generator had to provide, the real part of that power, is the sum of the real power consumed in the load, which is this one, plus the real power lost in the lines, and that's that part. You add those two together, and that is the real power that the source had to generate. And the ratio multiplied by 100 gives me 97.6% as the efficiency of the system. Before finishing, I would like to go over different ways of calculating the complex power. One way that we used in this example was V times I asterisk, and the other one which was also used for in this case for the power loss in the lines, but was I squared in magnitude times Z. There is a third way of calculating power in an impedance, and that is to take the magnitude of the voltage of the impedance, square it, and divide it by the conjugate of the impedance. For this example, I would like for you to just recalculate the load power, or for single phase, and then you can multiply it by 3. And using this formula, so you can take the 25.7 was the current, IA, squared times Z, 80 plus J60. That should give you the single phase power of the load. And if you do it with this last form of the formula, you should get the same number, and that would be the single phase line to neutral voltage of the load squared, just the magnitude, 2570 squared, over the conjugate of the load, which would be 80 minus J60. And check your results and compare to the single line complex power, which would be a third of this one. We have reached end of lesson 24. My name is Fouad Albandi. I'm a PE in electrical engineering, power engineering. You'll find my name and web address and email address on this page. Here is the web address, own-your-destiny.mylearnworlds.com, and my email address is almost the same, own-your-destiny@yahoo.com. I invite you to visit my website when you have the time. You'll find comprehensive modules on different topics of power systems engineering on that website. Thanks for watching this video. If you enjoy my presentations, please click on the subscribe button and the notification bell. I hope to see you soon in another one of my presentations.